Designing an interplanetary mission requires sifting through an astronomical number of possible routes. Finding a single viable path means running millions of rapid calculations to test different transfer windows, gravitational assists, and planetary alignments. But calculating these routes quickly isn't purely a mathematical challenge. The speed of the search is heavily constrained by the software pipeline executing those equations. This execution profiler shows a trajectory optimizer pipeline taking a candidate from Python and handing it to a C++ math engine. Every handoff costs time. Repeated millions of times, this transition overhead wastes CPU cycles, strangles parallel processing, and slows optimization to a crawl. The architectural solution to this friction is a two-part ecosystem: a native numerical engine called pykep-core and its exact Python equivalent, pykep-rust. This project is an independent, pure Rust port of the numerical core from PyCap version 3. It is a ground-up native implementation of the physics, rather than a surface-level API wrapper masking the old C++ engine. The objective is to completely rebuild the underlying architecture so that the Astrodynamics models execute with zero transition overhead. By keeping the memory entirely in Rust, pykep-core allows these orbital models to compose natively with modern parallel optimizers, like fcmaes-core. The optimizer and the physics engine operate within the exact same language space. Effectively solving trajectory optimization requires clearing the entire data pipeline. Architecture, rather than raw mathematical latency, dictates the practical speed of the search. Replacing a trusted numerical engine demands a strict, unforgiving data contract. Without absolute reproducibility, researchers cannot trust the trajectories they design. The pykep-rust numerical contract enforces binary 64 arithmetic and standardizes Cartesian states into a strict 6-component format, position and velocity, mapped directly onto exact 6x6 Jacobian matrices. It explicitly rejects non-finite inputs. Enforcing this exact layout guarantees deterministic, predictable outputs across every mission calculation. We can evaluate how this contract performs by looking at the first major phase of trajectory design, the analytical kernel, which handles the rapid screening of potential orbital paths. These analytical tasks execute closed-form equations. They include fetching planetary ephemerides, solving zero and multi-revolution Lambert arcs, and finding the exact transfer orbit over a given duration. This chart compares analytical kernels. Pure Rust matches C++ in Sims-Flanagan mismatch latency and is up to 3 times faster for analytic Jacobians. Rust leads because these mathematical kernels execute directly without runtime overhead. It achieves these speeds with zero startup cost, bypassing just-in-time compilation. For the initial analytical screening phase, the native Rust architecture delivers lower latency and completely avoids compilation overhead. The computational profile changes dramatically during deep mission design, particularly when calculating trajectories, where a spacecraft's thrusters fire continuously over long intervals. Continuous thrust is modeled by cutting the trajectory in half. The engine propagates forward from the start and backward from the destination, creating a 7-component mismatch vector where they fail to connect. Closing this gap requires highly accurate adaptive integration using complex Taylor series or DOP853 algorithms. Testing this deep integration workload reveals an honest engineering reality about where the original architecture retains a distinct advantage. This warmed Taylor propagation chart shows the C++ Heyoka engine is 2.8 to 4.5 times faster than pure Rust. C++ achieves this using LLVM just-in-time compilation to generate optimized code on the fly. Conversely, pykep-core skips the compiler, relying on fixed, immutable expression tapes. However, the C++ approach carries a hidden cost. That LLVM compilation requires a heavy 50 to 450 millisecond setup penalty the very first time it runs a model. The Rust port explicitly trades away that peak warmed throughput. It sacrifices absolute steady-state speed to eliminate the setup time and the complex deployment dependencies required by a just-in-time compiler. The architectural design forces a strict choice: pay the upfront time penalty for JIT-compiled peak speed in C++, or select pure Rust for immediate execution and deployment simplicity. This brings us back to the Python user experience. How can a Python script leverage this native execution speed without hitting the transition bottleneck we saw earlier? The traditional, flawed approach runs a single scalar loop. The script passes one evaluation from Python to native, waits for the result, and repeats the process thousands of times, hitting a language boundary on every single iteration. Pykep-rust breaks this cycle by implementing deterministic batches. This batching system lets Python hand off an entire NumPy array in a single transition, routing it into a parallel rayon pool. Inside the native environment, Rust releases the Python global interpreter lock. A cached thread pool then executes thousands of Astrodynamics evaluations simultaneously. Critically, the output array returns strictly ordered and deterministic. The indices match perfectly, ensuring the reproducibility vital for optimization algorithms. By consolidating millions of transitions into one parallel payload, Python users achieve native execution throughput without ever abandoning their preferred language. In Astrodynamics, a faster calculation holds zero value if a researcher cannot trust the output. This diagram shows the validation pyramid pykep-rust uses to prove its accuracy. The models are validated not merely by compiling successfully, but through multiple overlapping layers of mathematical evidence. The base layer ensures strict parity. It verifies every calculation against exact golden values pinned directly from the original KEP3 version 3 release. The middle layers add independent mathematical invariance, directly verifying the conservation of energy and momentum in orbit to ensure the physics hold true regardless of the reference code. Finally, the top layer guarantees cross-interface parity, ensuring that a Python script and a native REST application yield perfectly matching outputs in every scenario. A new numerical port becomes credible only when its runtime performance is backed by these independent layers of mathematical proof. Since the benchmark data proves there is no universal software winner, engineering teams face a pragmatic decision on which stack to deploy. The original C++, pykep, and Heyoka stack remains the correct choice for long-running, deep Taylor integrations, where absolute peak steady-state speed is the defining requirement. Conversely, pykep-core is the right choice for purely native Rust optimization objectives, simple cross-platform deployment, and tasks dominated by massive analytical screening. The most effective professional strategy is a staged workflow. This hybrid approach leverages both architectures where they are computationally strongest. Teams use the cheap parallel Rust kernels to rapidly screen millions of initial options. They then promote the few viable finalists into the warmed C++ engine for the final, deep optimization. True trajectory optimization doesn't depend on declaring one programming language superior. It requires aligning your computational architecture directly to the mission's physical demands.